We're going to talk about surface area today, using double integrals to find surface area. So we want to find, we're starting with a surface. Our surface is z equals some function of x and y. And we're assuming that, that z has continuous first partials. So z has continuous first partials on our region, and R is closed and bounded in the xy plane. All right, so let's draw a picture of what we're looking at so we can develop our technique for coming up with our surface area of this surface. So here are our axes. And we have some surface up here. And we're looking at a little piece of the surface up here like so. And we're going to say that this corner is at a point piece of ij where x, and we're going to talk about our x sub I and y sub j. So we're going to project this little piece of our surface down into the xy plane. So we're going to call this little element of area delta S sub ij. So this is our little piece of surface area. And we're going to project this down into the xy plane. Into our region. So in the xy plane we have a little rectangle. And the dimensions of our rectangle are delta x sub I and delta y sub j. And this corner here is at x sub I, y sub j. So the corner of that little rectangular region is at x sub I, y sub j. And we're going to sum these little surface areas over our region in the xy plane. And that sum is going to be the surface area of our surface over that region. Now we've talked about surface area in several different contexts this year so far. We talked about arc length, and arc length is related to surface area. So we talked about arc length in the plane. We talked about arc length with polar coordinates. We talked about arc length with parametric curves. We talked about surface area of surfaces of revolution. So far we've in order to find surface area, our surfaces needed to be surfaces of revolution, and that gave us a nice symmetry that allowed us to use the arc length when we revolved it about an axis to find our surface area. Now that we know how to do double integrals, it gives us an additional tool, and we can work with more complicated surfaces. But based on what we've done with arc length and surface area so far, and I know Scott mentioned it already, what form are you going to expect our surface area to take? What kind of expressions are going to be involved? Radicals. And what else? What do you think is going to evolve in terms of our surface? Squares of are derivatives. So it's going to have something to do with the derivatives, and they're going to have radicals, and we're going to be squaring things. So surface area integrals often are very, very messy. So let's take a look at our surface and figure out how we're going to write our surface area. What we're going to do is take this little piece of this little area element, and we're going to approximate it with the tangent plane. So let's zoom in on this little surface element and draw the tangent plane that has its corner, its tangent at point Pij, and we're going to use that as the approximation for the area of the surface, this little surface element. We're going to zoom in there. So here are axes after we zoom in. And our tangent plane is going to be like so. And I'm going to draw these in different colors because I'm going to do this. And we're going to make vectors out of these two sides of this little piece of the tangent plane. So here's our point Ij. We're going to call this vector A and this vector B along the sides of that little portion of the tangent plane. And we're going to project this down into the plane again. And this is the point x sub I, y sub j. And if I project this down and I go over here, and I project this over onto the x-axis, this distance is delta x sub I. And same thing if I go towards the y-axis. Oops. If I project this point down and I go to the y-axis, this distance is delta y sub j. So these vectors, we're going to let these vectors represent the sides of this small piece of the tangent plane. So this is a little rectangular, a little parallelogram that we make with the tangent plane, with the small piece of the tangent plane. And vector A is going to be the components of vector A are delta x sub I times I plus f sub x, the partial of x, at x sub I, y sub j, times delta x sub I in the k direction. So this is just our change in the z value of our function from point ij to the end of this vector. Does everybody follow that? Okay. And b is going along in the y direction, so this should be delta x sub I. And b is going to be delta y sub I j plus f sub y sub j, yes. Y sub j, j, plus f sub y, the partial with respect to y, at our point. Delta y sub j in the k direction. And the area of this little piece of the tangent plane is the magnitude of the cross product of A and B. So delta, we're going to call the area of this piece of the tangent plane delta t of ij. So the area of that small piece of the tangent plane, delta t, is the magnitude of the cross product of A and B. That's one of the properties of the cross product. So this gives us a way to analyze our surface area. So if we take the cross product, the cross product has a lot of delta x sub i's, delta y sub j's in it. So I'm just going to write out the result. A cross B is minus f sub x, x sub I, y sub j, I, minus f sub y at x sub I, y sub j, j plus k, and this is all times delta x sub I delta y sub j. So that's our cross product, and this should be a parentheses here. So our cross product comes out to be this, and the magnitude of A cross B, and this is where we get our radical, equals the square root of f sub x at our point first partial with the partial with respect to x squared, the partial with respect to y squared, plus 1, all times, and I'm going to call delta x sub I, y sub j, just delta A at ij. So that's my little element of area. And the total surface area is the sum of all of these small pieces of area over the entire surface. So we're going to sum these over the entire surface. We're going to take the limit as delta x sub I, delta y sub j goes to 0. So delta A ij is getting smaller and smaller and smaller. That sum is going to be our integral, our double integral for the surface area. So everybody follow how we come up with this. All right, so we can write our expression for our surface area finally. Surface area equals the double integral over our region of the square root of f sub x squared plus f sub y squared plus 1 dA. And just like we did for arc length and for surface area when we talked about it for surface area of revolution, we're going to call this entire thing, this radical times dA, our surface area element. So we're going to say S, if we want to write it shorthand, the double integral over R of ds. And this whole thing is ds. So again, very similar to our arc length in the plane, very similar to our surface areas of revolution with these radicals, or the radical with our derivatives, squares of our derivatives. And just like our arc length and our surface area that we worked with before, these integrals often are very difficult to evaluate. So the examples that we end up doing are pretty easy examples. Either that we can do with methods that we already have, or we might end up having to plug them into a calculator to evaluate the integral numerically. Yeah, Anne.
Why does this work? I'm imagining a sphere right now, and if we were trying to find the surface area, it would just be a circle, right, projected down. So I don't really understand how this works.
Okay, so the question Anne asks is she's imagining a sphere and how this would work. So let me draw a quick sketch of what we're talking about. So here we are in the XY plane, and I'm just going to look at this first octant. So this, where it intersects the XY plane, so it's going to look something like this, right?
Mm-hmm.
So what we're doing is we're dividing the sphere into tiny little pieces, like so. And then we're approximating that little piece with the tangent plane. And we're making the edges really small. So what we would do for this is we're going to add up all the areas of those tiny little pieces of tangent planes. This is our boundary in the XY plane. So we end up adding all the pieces of the tangent plane of the surface above that boundary. So we'd add up all these little pieces all over this entire little surface. And then if we just did this, if we set up the double integral for this, we could multiply it by 8 to get the area of the sphere. Does that make sense?
Yeah.
So we're just projecting that circle up, or projecting the surface down onto the circle to give us our coordinates in the XY plane. But we end up adding up all those pieces over the entire surface. Okay? All right, any questions on that? If you understand setting up the triple integrals that we've done so far, or I'm sorry, double integrals that we've done so far, this is just a straightforward extension of that. The only complication is in the evaluation. We end up with this in our evaluation. So let's look at a couple of examples of setting up these surface area integrals. So we want our first example. We want to find the surface area of our surface is f of xy equals 10x, I'm sorry, 10 plus 2x minus 3y. And our region is xy such that x squared plus y squared is less than or equal to 9. So this is our surface. So what is this surface? This is what we're interested in. A plane. So this is a plane, and our region in the xy plane is a circle. So let's draw our region. These are just like our other integrals. Draw our region. And I'm just going to draw a quarter of it. So there's our region in the xy plane. And this is a quarter of it. So how do we want to set up our integral? Based on this region. What kind of coordinates do we want to use?
We want to use XY coordinates. Those are always better.
XY coordinates are always better. For this particular integral, the XY coordinates are not better. I'll give you that hint. So let's use polar coordinates. Because we have a circle, I'm going to say use polar. And when we do the integral, I hope you see that it turns out a lot easier. So for a surface area, we need our partial derivatives. So the partial of f with respect to x is 2. Partial of f with respect to y is -3. So our surface area is our integral over our region of the square root of 2 squared plus -3 squared plus 1 dA. And we're using polar coordinates to make our lives easier. So we're going to integrate from theta equals 0 to pi over 2, and we're multiplying by 4, because this is a quarter of our region. 0 to pi over 2. What's that?
How do you know that it's symmetrical for? No, not the circle, the plane above it. Well, I guess just because it's a plane.
Yeah, so if our region is symmetrical, then we don't have to worry about what the surface is doing.
But what if it was like really wavy in like the first quadrant, but then flat in the second quadrant?
Then that would show up in our f sub x and f sub y squared. That would take care of that. So our radius goes from 0 to 3, and we get the square root of 14 r dr d theta. And that's an easy one to evaluate.
Well, can you just plug in the r d r d theta?
dA in polar coordinates is always r dr d theta or r d theta dr. That is dA in polar coordinates. And then I'm going to pull the square root of 14 out. 4 square root of 14. The integral 0 to pi over 2, 0 to 3 of r dr d theta. What's the integral of r dr d theta? It's just the area of the circle, right? So this is just the integral of dA, and our region is a circle. So the integral over the region of dA is just the area of the region. So this ends up being 9 square root of 14 times pi. What's that?
Multiplied by 4 step, right?
Oh yes, I forgot to multiply by 4. 4 times 9, so 36 square root of 14 times pi. Thank you, Ann. All right, let me do one more example, a little more complicated. Any questions on this one? All right, so our job this time, we want the surface area. Of the portion of the cone z equals 2 square root x squared plus y squared. Inside the cylinder, x squared plus y squared equals 11. So how are we going to set this one up? What is a function that we're interested in? The function, we want the surface area of the cone. And so what is the cylinder telling us?
On the region of the circle.
The cylinder's telling us our region in the xy plane. If I were to draw a quick sketch of this, we'd have something that looks like this. Here's my cylinder going up like so. And my cone goes up like this. And we have so we're looking at the surface area of the cone that's here inside the cylinder. So the cylinder is telling us our region in the xy plane. So the region, x squared plus y squared less than or equal to 11. What's that? I'm just saying that we're looking at the circle and everything inside. So that's our region in here. And f of xy is our cone. 2 square root of x squared plus y squared. So we need our partial derivatives of f. So f sub x is 2x square root of, x squared plus y squared to the minus 1/2. F sub y is 2y times x squared plus y squared to the minus 1/2. And our region in the xy plane looks like so. This is a quarter of it. This is x squared plus y squared equals 11. So we're going to use polar coordinates. So our surface area is going to be the integral, 4 times the integral. This is a quarter of the region. 0 to pi over 2. 0 to square root of 11 for a radius. Of the square root of f sub x squared plus f sub y squared plus 1. And our area element in polar coordinates are dr d theta. So we get 4 integral 0 to pi over 2, 0 to square root of 11. And if I square these, add them together, and add them to 1, this is nice because it turns out that this simplifies to square root 5. RD theta. And this one's an easy one to evaluate. So any questions? All right, I have a couple of questions for you. If z equals f of xy, and this is greater than or equal to 0 over r in the xy plane. My first question, is it possible for the surface area to equal the area of the region of that function? Is it possible for the surface area of this function to equal the area of the region?
Yes.
And if so, how? Okay, perfect. So if you have a plane parallel to the XY plane, the area of that plane is going to be the area of the region that you're interested in. Is it possible for for the surface area to be greater than the area of the region? Yes. Plane raised up half a unit? So we're talking about the surface area. Surface area. Can the surface area of the function be greater than the area of the region in the XY plane? The area of the region in the XY plane. What do you think, Andrew? Let's discuss this. Anybody? Okay, so Scott says wavy. Isn't the surface area usually going to be greater than the area of the region?
Yeah.
The area of the region is going to be a circle, a rectangle, something in the plane, but if you have some surface, the surface is kind of stretched.
Mm-hmm.
Can the surface area of the function be less than the area of the region?
Yes.
Anne says yes. What, do you have an example, Anne? No? You just wanted to to be different? The surface area of the function can't be less than the area of the region. It has to be greater than or equal to. All right, homework. On these problems, a lot of times, often, the difficult part is simplifying the f sub x squared plus f sub y squared plus 1 so you get something that you can integrate. All right, there you go.
So would you suggest multiplying it all out while it's showing x and y and then seeing if you can convert it to polar?
Here.
And for most of them, we could probably convert it.
If your region has like circular symmetry, usually it's going to be easier to do in polar coordinates.